Hey everyone, good morning. My name is Shreyans Doshi. I hope everyone is having a great time here at the conference. Yeah? Awesome. So, my talk is labeled Perfidious, make PE backdooring great again. And even though we'll be discussing a technique that could be used to possibly backdoor PE files, I would like to make sure that you keep an eye out for the bigger picture, which is the framework and the library itself, right? So, who am I? My name is Shreyans Doshi. I am a cybersecurity graduate student at UMD and I'm a teaching assistant for the reverse engineering course at UMD. I have previously worked as a malware research intern at Cybrary where I started developing this project, and I like malware analysis and reverse engineering. So that's enough about me. I'd like to know something about you. So how many of you all are interested in reverse engineering, malware analysis, stuff like that? Oh, awesome. Great. So before we get started into what Perfidious is and what it is trying to do, it is important to understand the context under which this entire thing was developed, right? So it was summer 2019, May, August period. I started working at Cybrary as a malware research intern, and my manager for the project basically said, okay, we want to develop a project that could be used to develop malicious files out of benign PE files, and you can maybe develop parsers for source code and plug it into a machine learning system that could automatically generate malware samples, right? That was his initial idea. Now, I had two questions regarding this. Is this legal for me to work on? Because what I would be essentially doing is developing malicious software that could be used to bypass the endpoint detection systems that were currently in place, right? I do not want to get arrested by the FBI. The second question was that how would I go about getting the source code for all these malware samples, right? Because if you have worked in the field, you know that malware source code is something that is really hard to come by, right? And you would need enough source code to be able to, even if you had parsers in place, right, that could parse all the source code to develop new malwares, you would need enough samples that could train a machine learning model on it, right? Now, as fate would have it, the manager basically left the company for another company, and I was left with the project to do whatever I wanted to do with it, right? So I had two choices. Basically, I could idle away my time at Cybrary, or I could develop a project that could be a logical conclusion to what he started, right? So that is where Perfidious comes into picture. Now, before you can get into Perfidious, it is important that you understand what a PE file format looks like, right? Because that is the input to Perfidious. So this is the basic structure of a PE file. You have the DOS header followed by the DOS stub, followed by a rich header which may or may not be present, followed by the PE signature, followed by NT header. These together compose the entire PE header that we know about. This is followed by the section header and the actual sections, right? So before we get into each of these components of a PE file, it is important to understand what these terms mean. Raw address. So raw address space, as we know, starts at 0. This is basically the raw file size of the actual PE file that we have. It starts at 0. There is virtual address. Virtual address is basically the address at which each of the components in the raw file are loaded in memory when the file is run. So raw addresses usually start at that hex number. Then we have something called RVAs. Now RVAs are important to understand because RVAs are something that the PE file uses internally to map addresses, right? So whenever we have an RVA present inside the PE file, we need to convert it into a raw address to find that data structure on the file itself, right? So this is the formula that we utilize. Now, the first data structure present inside a PE file is the DOS header, right? DOS header contains a ton of different internal components. The main ones are highlighted in yellow. eMagic is the MZ signature that we see at the beginning of any PE file, right? This basically identifies that this file is a PE file and it can run with the help of Windows Loader, right? Checksum. Checksum is basically the checksum of the PE file. This helps us. This is basically one of the first checks that you need to make sure that the checksum of the PE file is same as the checksum mentioned in this particular field. That basically tells you that this file has not been tampered with, right? The ELF new basically tells us the offset to the extended header, which is where the actual PE file begins from. DOS stub. How many of you all have participated in any of the flare-on challenges by FireEye? So they are basically the reverse engineering Olympics, you can say. They are some of the reverse engineering challenges that FireEye puts out every year. In 2016, they put out a challenge which was basically a DOS file that was that basically said, so once you completed the reverse engineering challenge, when you executed the file, it basically said that this file cannot not be run in DOS mode, right? So it was basically a DOS program, which was present inside this DOS stub. So DOS stub can contain an entire DOS program hidden inside it, or it can contain a program which runs and says, okay, this program cannot be run in DOS mode when you try to execute it in DOS mode, right? Rich header. Now, rich header was previously unknown data structure that was discovered around 2015-2016 timeframe. This was previously used by Microsoft in order to find various malware groups that were utilizing, because this data structure contains information about the compilers and the linkers that were used to create the PE file, right? So this could be used as a mechanism to develop signature for various malware groups that were writing malware samples, right? So this is another important data structure that one needs to make sure to keep in mind. PE signature. This is the PE followed by null null. This is the place where the actual PE file should ideally begin from. Like the data structures present previously are basically used for backward compatibility reasons, right? We don't really need those data structures. This is followed by the NT header, which is composed of the file header and the optional header, which links to the data directories. Now, file header. How many of you all know what UWP means? Yes. Platform. Yeah. So why do we have UWP? Like why does Microsoft need UWP? What is the agenda for having UWP in place? Exactly. Exactly. So what Microsoft is ideally trying to do is have a single file format for each of the various applications that can run on every device that they have. So they are trying to have some sort of uniformity throughout the various devices that they can support on their operating system, right? So in order to do that, the files need to have enough fields and enough information in place that can help the programs run on various Windows loaders that exist on those platforms, right? So file header basically contains the information about all those things. It contains the machine code basically, which says that, okay, this is the architecture on which this particular file is supposed to run on. It has the number of sections that it contains, the time date data, the time date stamp. Anyone know what that time means? January 1st, 1970. Why is that time? Like, why that specific time? So that basic that date, that timestamp is basically called the epoch time, right? That is considered as the beginning of time. So that particular field calculates the time delta between when the program was actually compiled with that minus the that particular timestamp, and the time delta that you get is basically stored in that particular time date stamp field. So you can use that field in order to find when this particular program was compiled, right? Now, all the other data structures after that contain information that is important as well. Another important field is characteristics, right? Characteristics basically gives you information about what kind of file this actually is, right? Whether it's a DLL, it's an exe, what kind of permissions this file has, and stuff like that. Next, we have optional header. Even though it says that it's an optional header, it's not really optional. It contains information about the base of code. Base of code basically tells you at what point inside the PE file the text section begins, right? Text section is the place where the actual code for that particular program is stored, right? The image base basically tells you which virtual address is used in order to load this particular program into memory, right? So even though it says that it's an optional header, it's not really optional. Now, once this optional header is completed, it's followed by the data directories table. Data directories table basically contains information about the size of the data directories and the raw virtual address at which this particular data directory is loaded, right? These are some of the data directories that are commonly found inside PE files. Not all of these data directories will be contained inside a PE file, but some of the common ones which I'll explain are the ones that are usually found inside all these PE files, right? Export table. Now, can anyone of you tell me what an export table means? Why would you have an export table inside a PE file? What could it contain? Anyone? So, as the name suggests, export table basically contains information about the functions that are exported by this particular PE file, right? Now, PE files not necessarily are executables, right? They can also be DLLs. DLLs are basically dynamically loaded library, linked libraries, right? Now, DLLs basically contain information about the functions that it exports. So this table can be used as a reference to find all those functions and the addresses inside the DLLs where these functions are stored, right? Then we have the import table. Import tables are usually present inside the PE files that are EXEs. These basically give you information about all the functions that are imported by that EXE from the various DLLs and the addresses at which these functions can be found. There are multiple sub data structures as well found inside for the import tables. We'll not go into that. Resource table. Why would you need a resource table inside the EXE? Inside any PE file, why would you need a resource table? Now, when we usually think about programs, they need not always be a CLI program, right? They can be GUI programs as well, like games, right? You'll have a ton of different resources like images, song files, icons, stuff like that, right? You need to have a resource table that can be used in order to index those resources, right? So that the program, when it runs, it can find those resources at those memory addresses. Resource table contains all that information. Exception table. Exception table contains information about the various exception handlers that are present inside the PE file, right? Whenever an exception is triggered, it goes to this exception table, finds out what function it needs to execute for that particular exception trigger, and it executes that. Certificate table. Certificate table contains information about the certificate that is used to sign this PE file, right? So say you had Microsoft certificates lying around, right? You could sign your own executables with those Microsoft certificates, and your certificate table would contain the Microsoft certificates, right? Then when you ran those on Windows, you'd never encounter the yellow box that you get when you try to run files that are not signed by Microsoft, right? Yeah, like this program has not been signed by Microsoft. That is basically how you can bypass the certificate table check. Debug table. Debug table is usually stripped inside most professionally put out PE files. Basically, this contains all the debug information, like all the debug flags, all the breakpoints that were used when you were debugging the PE file. TLS table. Can anyone of you tell me what TLS table means? What it could have? What TLS means? What is TLS in this context? It's not networks. So what does TLS mean? Anyone? So TLS basically stands for thread local storage, right? Most operating systems that we have today are multi-threaded operating systems, right? Programs use this multi-threaded capabilities. So TLS table basically stores information about various variables inside various threads inside your program, right? This differentiation is important because otherwise we could not have that multi-storage capability where same variable is used for multiple threads, right? All that information is stored inside the TLS table. Import address table is basically same as the import table until it is loaded in memory, at which point the addresses are replaced by the actual addresses in memory. Now this is followed by the section header. Section header contains information about the section itself that are present after it. It contains the name, the virtual address, the size of the raw data, pointer to that raw data, and the characteristics. Now, can anyone of you tell me why characteristics are important for various sections inside PE file? For those of you who have worked with PE file, why do you need characteristics for each of these sections? It's just a stream of bytes, right? Why do you need characteristics? Yes.
Anything to do with like read, write, execute?
Exactly. So depending on which section is present inside the PE file, each of these sections have their own permissions, right? Not all the sections present inside PE files have execute permissions. Only the text section can be executable, but the text section cannot be writable, right? Because you don't want your text section to be replaced by another text section, right? So that is why you need characteristics which can highlight what kind of permissions are contained for that particular section. Now, the current code injection techniques that we have, one of the most common ones is custom section addition, right? This is something that if any one of you have gone through OSCE, this is one of the techniques that is discussed in that course. So you basically add a section at the end of the PE file. You create an entry inside the section header for that new section, and you give it the read, write, execute permissions, right? Or whatever permissions that you want to give. And then you basically change the entry point of the PE file to point to that new section. What this does is, instead of executing the text section when you try to run this program, it will execute the new section that you added at the end. Now, The disadvantages of this approach are basically it is very easy to detect by most endpoint detection systems, right? Because not in most PE files, only the text section is the section that contains execute permissions. So the endpoint detection system can basically just check for the sections that have execute permissions, and it can say, okay, this section is something weird. I basically want to flag this PE file, right? So the stealth gain versus the time required to correctly implement this thing is way too low, right? So what is the other approach you can take? PE code caving. Can any one of you tell me what a code cave is? What does it mean to be a code cave? Like what could a code cave be? What do you understand by that word? So PE files are basically stream of bytes, right? Not all those bytes are filled with information that is important for that file to run, right? There'll be a stream of nulls that are present inside various locations inside PE files, right? Those nulls might not be utilized. Those are called the code caves, right? And that can be used in order to fill your malicious code inside, right? So how PE code cave works is you basically find the code caves that exist inside the PE file. You try to find those code caves that exist inside sections with execute permissions. That is basically the text section. If you find such a code cave, you replace the nulls with the malicious code, and then you change the entry point address of the entry point to point to your new shell code that you injected, right? That is how PE code caving works. Can any one of you tell me what is the problem with that approach? Like, what could be the problem that you could face when you try to inject malicious code inside PE code caves? Not really. What are some of the limitations of trying to inject code using this technique? No, it will function. So when you talk about code caves, there is a limitation of size that is present for the code caves that you have, right? First, you need to find code caves inside the PE file. Say you were able to find those code caves. Then you want to find a code cave that is large enough to store your shell code. Then you need that code cave to be present inside the executable section as well, right? So this technique is not really this is not something that you can execute. This is not something that you can do for each and every PE file that you have, right? This is these are some of the disadvantages of this approach, right? You need to be able to find code caves inside the PE file. You need to find a code cave that is large enough. You need to find a code cave that is in the executable section, right? So why not just edit the .text section instead? What could be the problems that you could face? The .text section has the execute permissions that we need. It has all the necessary things that we require. Why not just do that? Say you were able to edit the checksum. That is one of the disadvantages, but say you could edit the checksum. What would be the problems that you could face when you change the text section? Yes?
Did you say the text section is not writable?
Yeah, but it's just a stream of bytes, right? Say you were able to find the text section inside the PE file. You could basically just pull it out and
changing the offsets for everything inside the text section.
exactly. That is one of the reasons why this has been really difficult until now, right? Because when you change the text section is usually the first section that exists after the section headers, right? So when you change that, you basically move everything that comes after it, right? So you need to be able to map everything inside the PE file in such a way that if you make one change inside the PE file, all those changes are reflected back into everything that follows, right? That is where Perfidious comes into picture, right? What Perfidious is trying to do is Perfidious is trying to fingerprint the PE file and convert it into a Python-based class, right? So each and every data structure that is present inside the PE file is mapped into a class structure. And whenever you make a single change inside any of the structures present inside that class, you basically create appropriate changes inside for the sections that are dependent on that as well, right? So what you do is you use a function to directly import malicious code. The Perfidious extracts the text section of the PE file and combines it with malicious code in such a way that it changes it via the control flow graph jumps, right? So this is basically even more difficult to detect because now you don't have a single blob of malicious code present inside your PE file, right? You have connected those individual malicious chunks via jumps. right? So you don't have a single blob of code that can be detected via signature detection mechanisms, right? So that is what Perfidious is trying to do. Now, advantages of this approach: it is relatively difficult to detect it statically if it is done really well and really right, right? The malicious code itself is split into smaller pieces, so it is difficult to detect. All the other parts of PE file are left relatively unchanged, right? You're just making changes to the .text section, and you're performing the individually dependent changes inside the PE file, but not the entire PE file is being changed, right? So it is relatively unchanged. So these are some of the advantages of this approach. How would you go about preventing such kind of detection, like injection? How would you prevent this kind of injection? What would be the easiest way in which you could prevent this kind of injection of PE files on your system? Like, how do you detect such an injected PE file? So one of the easiest approach would be to only allow whitelisted software on your network, right? Only allow whitelisted checked software that has been verified that, okay, this software comes from this particular author on your network. That is the easiest approach to basically stop malware on your network, right? But that is not really feasible for most enterprise networks. So the next approach would be to have dynamic analysis on all PE files that come through your network, right? That is an approach that you can use to detect, because in dynamic analysis you are basically detecting the control flow of the program itself, right? So if it does something malicious, it can be flagged. One of the third approaches that you could use to detect such kind of injection is that you can use something called a graph hash, right? This is something that I came across while I was in Singapore at Hack in the Box. So the researchers there basically suggested developing a hash for the control flow of the program, right? In that way, basically, if the control flow of the program changes, the corresponding hash changes as well, right? So you can use that hash to detect basically how different a particular program is from another program, right? So those are some of the techniques that you can use to detect such kind of an injection. Now, even though this program is not completely ready, I'll give you a demo of how it works. So when you right, so this is how it works. You basically have the PE class structure, you pass into one of the PE files that you have, and then when you print that particular class structure, it basically shows you all the things that it found inside it. It found the DOS header, it found the DOS stub. It did not find the rich header because it does not exist for this PE file. So it creates a PE object at that particular address. Now, if I try to print a particular data structure, this is what it does, right? It has taken each and every field inside the DOS header structure, and it has basically highlighted all those fields in this particular format. It even calculates the checksum for these individual data structures that is present inside the PE file. Now, can any one of you tell me why that could be a useful thing to do? Why would you want individual checksums for various data structures inside the PE file? Anyone? Yeah, so basically you could use it to detect at specific granular level which part of the PE file has been changed, right? You can use this in order to detect injections in various parts of the PE file, right? So this is one of the things that it can do. Apart from doing this, so this is the end, this is sort of the intermediate end goal of this project, right? So what I'm doing here is I'm printing the original DOS stub message of this particular PE file. I'm changing that DOS stub message using just the equal to sign and replacing it with BSides Charleston, and then I'm printing it again. Now, if I try to run this, this is what happens, right? This is the original message that is present inside the PE file, like any other PE file, right? This program cannot be run in DOS mode. But now this message has been changed to BSides Charleston in 2019. So this is my intermediate goal for January, February 2020, that I should be able to do this for each and every data structure that is present inside the PE file, right? Say I wanted to change an address to a particular function inside the import table. I should be able to do that using just the equal to sign, right? So what this does is it gives me accessibility to every data structure that is present inside the PE file. The next thing would be to develop a machine learning algorithm that could automatically develop class-based structure for the malware samples that are passed into this project, and then find out, okay, what changes I could make in order to make a particular PE file undetectable for the current endpoint detection systems, right? Once I have fingerprinted the entire PE file, that would be the next logical step to go about doing this. So that's it from me. Thank you. Any questions? Yes. Sorry? So currently this thing is not open source because I'm still trying to, so around January time I'll be open sourcing this project because that is when I'll have completed the fingerprinting part of it. After that, you could basically help me develop the machine learning part of things. That is the next phase of this project, or you can basically use it to, it's just a Python library, right? You could develop your own detection systems using Python for it, right? You could plug it at the end of your network and basically say, okay, I want to detect these kind of injections into a particular structure inside the PE file. You can use it to develop your own detections like that. Like that is what I have in mind until now. Any other questions? Awesome. Thank you for your time. I have backdoor and breaches card.